Okay, so this one is on the Bernoulli equation. And in the last lecture, we derived this thing, the Euler-S equation, and we were able to integrate that. It was all DDS's, and we integrated it, and we got this. We got pressure plus 1/2 rho v squared plus gamma z is equal to a constant, which is commonly referred to as the Bernoulli equation. And these terms have meanings. This came out of F equals ma, and we integrated it in length. So it's like an F times a dx, which is energy. It's work. It's one of our usual physics ways of writing what work is. An integration of F times a d length, and the S is like a length. And so we expect these things to have the units of energies, which is like a work does. And in these, we can look at them and we can see they actually correspond, in some cases, very specifically to different sorts of energy. In other cases, less so. But let me point this out. This one is a 1/2 rho v squared, and a rho is a mass per volume. So it's 1/2 mass v squared. That's kinetic energy, and it's kinetic energy per unit volume. So that's kinetic energy like. And we just remember, I'll put it in quotes, and you just remember it doesn't exactly match the units of kinetic energy, but it is a kinetic energy per unit volume. And this one, gamma is rho g, z, rho gh. mgh is kind of our standard way of writing potential energy, gravitational potential energy. When it's m over volume, it's a potential energy per unit volume. And so this one is like potential energy. And pressure is kind of the new one, but it's not that new. And one way to interpret it here is it's a capacity of the fluid to do work on itself. And so to do work. It's sort of on self. I'll put that in quotes because it's kind of a silly thing to say. But a fluid at high pressure can sort of do work on itself and get a high kinetic energy. That's what that means. And I want to make these concepts a little bit more concrete by considering a specific example. And I want to say that we have some sort of syringe thing. And we're pushing on it with a force. You can think of a doctor's office type syringe with maybe not a needle on it, but this is how it's drawn here. And let's say it has fluid in it, and you're squirting it out, and it's rising up to some height. And if you actually have a hypodermic needle type syringe, you can squirt it quite a way. And I'm going to label some points. 1, 2, and 3. So 1's inside, 2's here, 3's up there. And let's say that there's this height. And let's say that h is large. Compared to that. And so you're squirting this, and it's almost reaching the ceiling, and it's a little bitty syringe thing you're squirting. It's just not drawn to scale here. Why I want to look at that limit will be pretty obvious here in just a moment. And I want to consider these three terms and their roles of kinetic and potential energy as we move between 1, 2, and 3. When I say move between 1, 2, and 3, we have to recall one of the principal assumptions made in deriving the Bernoulli equation, and that one being that it's on a streamline. This is an equation that's good on a streamline. We integrate it in S, so that means integrating along a streamline. And in this case, our streamline might be, let's say there's one that starts out here and goes up to here. So that's our streamline. When we do Bernoulli equation problems, I'm going to say step 1 is draw a streamline. I'm not going to really talk about any other steps. If you're lost in how to get the answer, drawing a streamline is a very good first step. So there's our streamline of what this is. I'm going to make a little table here. I'm going to give it a P. I'm going to give it a 1/2 rho v squared. I'm going to give it a gamma z. And I'm going to want to look at points 1, 2, and 3. I guess I'll put a line down here too, separate them out. So the idea is I want to discuss kind of the conservation of energy that's more or less embodied in the Bernoulli equation here. And at point 1, let's label these potential energy, kinetic energy, and then I'll put work in quotes here. Work potential. It's not really work. You get a high pressure in there. You're putting a lot of F on this. There's an area, force per unit area. It's going to give you a pressure, and that's nominally high. So let's just say this is high. The plunger on the syringe will move very slowly compared to how fast the fluid is coming out. And so this one's about equal to 0, let's say. And we can measure z from some coordinate. Let's say it's right here. And all these lengths here are small. So 1 is effectively close to 0, 2 is right at 0, 3 is much, much bigger than 0. And so the potential energy here is also about 0. Now as we move from 1 to 2, the fluid does work on itself. It converts its pressure. It uses its capacity to do work. It's stored pressure to accelerate itself. We've put on high pressure with the force on the syringe, but the fluid accelerates itself. And so at 2, we have high kinetic energy. And we still have about equal to 0 or equal to 0 potential energy. And a hard thing, a concept here, is that the pressure is also about 0 or atmospheric. And this was a problem on the first problem set we did, where there's this jet of liquid, and we asked the question of how much is the pressure inside that jet elevated, and there's really nothing about it that elevates the pressure except the surface tension, and those are always really, really small numbers, a tiny, tiny fraction of an atmosphere. They weren't significant compared to the pressure that was in here. And so it's in contact with the atmosphere, and that's sort of the way to say it, why it has about 0 gauge pressure. I'm going to cross all the zeros now that I crossed that one. And now as we go on up to 3, think about what happens. There's nothing different here between you throwing up a bit of mass and it going up now, the trajectory stopping at the top and then coming down. Fluid does the same thing. It squirts up. Every little particle is just a little bit of mass. It stops at the top and comes down. And so its velocity at the top is about 0 or equal to 0. Its potential energy is now high, right? Because h is a big number. That's large compared to everything else here. We're calling that a large number. The fluid's also still right in contact with the atmosphere. There's no reason for the pressure to be high except for small effects such as surface tension. And so we're going to say, again, 0 gauge. And so we have this exchange that occurs in this and in all of these examples, is that there's this principle of conservation along a streamline. It manifests itself here as an energy conservation. And you exchange different parts of it, and that's what Bernoulli equation is. And so pressure in this case becomes kinetic energy, becomes potential energy. And we shouldn't be at all surprised that, that things would happen or occur in that way, given our understanding of what energy conservation is.